So let's do this probability analysis. So now what is the goal? The goal is we want to come up with the coloring of the vertices of the graph with k colors, and again no, we want to come up with it, and the way we are coming up with it is by looking at this search space of all possible k colorings of the graph and choosing one coloring uniformly at random from this search space. Okay? Or in other words, you can look at it like this. You have the vertices of the graph v1 to vn. For each vertex, give it color 1 to k with uniform probability. That means you give it color 1 to k with probability exactly equal to 1 by k. So what is the experiment? For each v in vg, v, and for each I in 1 to k, v gets color I with probability 1 by k. So this is the experiment that I do, and after the end of this experiment, all the vertices of the graph are colored with some number or some color from 1 to k. Okay? And what is the goal? We want to compute that what is the probability that basically suppose there is a k path in the graph. So suppose there was a k path in the graph, we want to compute what is the probability that this coloring would color this k path colorfully. So in other words, what is the probability that all the vertices of this particular k path will get distinct colors in this coloring? That's the probability that we are interested to compute, right? If this probability is good, then our algorithm will be a good randomized algorithm. Right? So probability that C, so let's say this path is P. We want to compute what is the probability that C, yeah. So let me just use this term, C makes P colorful. This is the probability that I want to compute. Okay. The experiment is clear. I have told you what I want to compute. Now, what is this probability? K factorial by k par k. Why? Okay, yeah. So as he says, it's it's that. So if okay, the way he's saying is, if you want to make a particular path colorful, how many ways can you make that particular path colorful? So a path is colorful if it is using all the colors. So as we just saw, to solve the colorful k path problem, the number of ways in which we can make this path colorful is k factorial ways, depending on in which order do I color the vertices of this path. And the total number of colorings that we can give to this to the vertices of this path are k par k colorings. The total number of vertices which might not be colorful are, every vertex of this path can get colors from 1 to k. There are k such vertices, so k par k. Right? So this is one, but usually, as Sunil usually points out, so when you are writing probability, just try to be formal and try to use the appropriate formula to compute the probability. So even if you were using the formula, we will get the same answer. So what is the formula if you have a uniform probability distribution? What is the probability that a particular event occurs? There is a standard formula for it, right? The probability that a particular event occurs is, so you have a search space, look at all possible outcomes and look at all possible outcomes which are good, in which that event occurs, right? So what are the all possible outcomes of this experiment? The all possible outcomes are all possible colorings of this graph using k colors. And what are the favorable events, or what are the good events? The good events are the ones in which this particular path gets colorful, gets distinct colors, right? So the probability is, so the formula for probability is total number of favorable, so favorable outcomes by total number of outcomes in this experiment that we have done. And what is total number of outcomes? What is a favorable event for us? A favorable event for us is that coloring which makes this particular path P colorful, right? So again, so if I have to use this formula to get probability, what will that be? What is the total number of outcomes? Why is it K par K? But the coloring that I am giving, like what is my experiment? My experiment is not just coloring these K vertices, my experiment is coloring all the N vertices of the graph, right? So how many possible colorings will I have? Like what is the search space of this probability distribution? K par N, right? The total number of, so let me just write this, we will eventually come to this expression that you just told, but so this is, so total number of outcomes is K power N, right? And what are the total number of favorable outcomes? They are those colorings on these N vertices which make these particular vertices of P colorful, and there are K vertices in P. So, yeah. So as he says, it's K factorial into K power N minus K. And why is this so? Which make it colorful.
Other vertices we don't mind about the colors of other vertices.
Exactly. So as he says, so what are the good colorings for us? Except for these vertices in this path, we don't care what the other vertices get, right? So the other vertices could get colors from 1 to K. So the total number of other vertices is N minus K. So for these N minus K, these can get colors any colors from 1 to K. So it's K par N minus K into the colors that these vertices on the path can get. How many different colorings can a vertices on these path get? Some K factorial, right? Because we want to make it colorful. So into K factorial, right? And this again comes out to this, right? So the probability, so if I choose a coloring uniformly at random, then with probability K factorial by K par K, this will this will be a good coloring for us. Good as in it will if there was a K path in the graph, then it will indeed make it colorful, right? Now, yeah. So, does anyone know does anyone know if a way to get, yeah, to basically write this expression more neatly, let me say like that. So basically, does anyone know an upper bound for K factorial? Upper bound, just an upper bound. K factorial is at most anything. Go ahead. So I'm just asking, usually when you say you have a K factorial this thing, you can upper bound it by that, yeah, that's like that everyone knows, right? It turns out that there is also a lower bound for this expression. Again, we will not prove it, so there is something called Serling approximation, and what you can prove is we can also prove a lower bound for this term. And what's that lower bound? That lower bound is, so basically when we upper bound it by K par K, this is not very bad in the sense that there is also a lower bound for it, which is K by E par K. And what is E? E is this exponential constant, 2.718, I think, yeah. So there is also a lower bound for K factorial, which is this. Again, we are not going to prove this, but this is true, okay. So if I use this lower bound, can I lower bound this term that I've got, the probability that I've got, right? So yeah, let me just write it here. So this will be at least 1 by e par k, right? This probability, right? So what have we proved? That if I take a coloring uniformly at random, then this is a good coloring for me. This is a good coloring for me with probability at least 1 by e par k. Okay. So what is the result that we have proved about our k path problem? So if I want to solve k path problem, what will I do? I'll choose a coloring uniformly at random with probability at least 1 by e par k. It will be a good coloring in the sense that if there was a k path, then it will make that k path colorful, right? So now if I solve the colorful k path instance, if it says yes, then we all know there is always a k path in the original graph. But if it says no, then it is outputting the correct. It is outputting correct with probability at least 1 by e par k. So what does it mean? If it says no, we want to say it is correct. If it was no here, then it was a no in the original graph. Or in other words, if there was a k path here, then it says yes. So if there was a k path there, it would say yes with probability at least 1 by e par k, because this is the probability with which this coloring would have colored this k path colorfully, right? So our algorithm is correct. It's basically the error is only one sided. So if it outputs yes, it's always yes. If the colorful k path gives you a colorful outputs yes, if it gives you a colorful k path, then you always have a k path. But if it outputs no, then it might be making some error, but it makes that error with let's say it doesn't make that error a lot of times. So in at least 1 by e par k, with probability at least 1 by e par k, it would not have made that error even in the reverse direction, right? So this is so we have some randomized algorithm, but this is not a good randomized algorithm because like there is a notion of efficiency in polynomial time algorithms. So randomized algorithm is good if its success probability is at least some constant, or its failure probability is at most some constant. Okay, so this is the notion of a good randomized algorithm. And if you see here, the success probability is at least 1 by e par k. It's not a constant. E is a constant, but e par k is not a constant. K is dependent on k is what comes from the input. So as k varies, this will not be this probability is not good, right? So basically, what is it saying? So if I give larger and larger values of k as input, the success probability becomes smaller and smaller, right? So that's the reason when we are designing a randomized algorithm, we want its success probability to be constant, because we can give it any arbitrary instance as input, right? And if I give it an instance where k is very large, then this success probability is very low, right? So this is not good for us in that sense, and hence whenever we try to design randomized algorithms, we try to design algorithms so success probability is some constant. Okay, so we have a randomized algorithm, but that's not really good. So if we want to make it good, what do we want to do? We want to make sure that whenever it makes if it makes a mistake, it does not make a mistake too often, or the probability that it makes a mistake is at most some constant is what we want, not e par 1 by e par k. So what can we do to boost this probability up? So this is clear. Let me just go to the next slide. So what have we done? We chose C uniformly at random. So C was the coloring that we did a random experiment, and we have this coloring, and we know that probability that C makes a k path P in G colorful is at least 1 by e par k. So that means C, let me just say this is the good event for us. So let me say C is good with probability at least 1 by e par k, and so we know that C is bad with probability at most 1 by minus e par k. And what we want is, we want an algorithm which is bad with some constant probability. Okay, So what can we do to, basically you want to boost this probability up. Have you guys seen a probability before as, let's say, a formal course or? So, okay, yeah, so I don't remember, was such a thing taught to them? Boosting probability, it was? Huh? Okay. Yeah. Yeah. So what we did was, we started with the k-path problem. We chose the coloring uniformly at random and ran this experiment and ran the algorithm for colorful k-path, right? And this algorithm was wrong with probability at most 1 minus 1 by e power k, right? So let's do the following. See, if the algorithm outputted yes, we know that it's always a yes. If it outputs a colorful path, it's always a colorful path. If it outputs no, what I go is, I forget about this no. I go back again, compute a new random coloring again, and then again run the colorful k-path instance on this random coloring. I do that again. Again, if it gives me a colorful k-path, I'm happy, yes. Otherwise, it says no. And I'm adamant, I keep on doing this. And I just want to check, like it's like, I just want to check your patience. Till when are you going to lie to me? It's that sort of a thing, right? So I keep on doing this. Of course, I can't keep on doing this forever because my algorithm has to have a certain kind of running time, okay? So I keep on doing this. Let me say I keep on doing this, or I repeat this experiment e power k times. So what does it mean? I had to solve the k-path problem. I construct a coloring C uniformly at random, and then solve this colorful k-path instance by giving this coloring as the input. If it outputs yes, I output yes and I stop. If it outputs no, I repeat it. Compute a new coloring uniformly at random, again run it. If it says yes, fine, repeat it. And I do this e power k times, okay? What is the probability that the algorithm would have said no in all the iterations? It is what? Sorry?
1 by e.
1 by e. Why?
1 minus 1 by e to the power k can be bounded by e to the power minus 1 by e to the power k.
So we'll worry about this bound. Like, what is the expression? How do you get 1 by e? What is the first step of the expression?
So 1 minus 1 by e to the power k is less than equal to e to the power e to the minus 1 by e to the power k.
Yeah, so yeah, we'll worry about substituting it later, but the expression is 1, you're saying it is 1 minus 1 by e power k to the power e power k is what you're saying, right? Yeah, so what is the probability that C is bad in all steps? Take the union bound. If C is bad in all steps, that means C is bad in the first iteration, C was bad in the second iteration, C was bad in the third, and C was bad in the e power kth iteration, right? And the probability that in any iteration C is bad is at most this. So the probability that C is bad in all iterations will be this plus this plus this plus this. Oh no, sorry, it's not a union bound, it's and. So when do we say no? We say no when this coloring is bad in all the iterations. It's bad in the first iteration and it is bad in the second, because if it was good in any one, I would have said yes, right? So when I say no, it's bad in all the iterations, and when we do these experiments, they are independent experiments. So when I compute this coloring for the first experiment, that's we computed, and when we do it for the second, it's independent of what I had computed in the first step. So these are all independent events. So the probability that C is bad in all the iterations will be the probability that C is bad in the first to the power number of times I have repeated this, right? And now you know it, but do you know any way to bounce this expression? What is this expression? So basically there is this thing. So if you look at this e power x term for any x, there is this exponential series, right? For e power x, you can write this, this is equal to some 1 plus x plus, sorry, yeah, plus something, 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 I don't know. But it's definitely 1 plus x plus some more things, some more positive things, okay? So, using this exponential series, one can always say that e power x is at least 1 plus x, right? I can forget about this term. So, it is at least as big as 1 plus x, right? So, always, so this is another thing that one should always remember, that e power x can always be, or 1 plus x can always be upper bounded by e power x, okay? So, now I want to use this expression to simplify this. And how will I simplify this? Look at, like, this can be written as 1 plus, so consider this as x. So, 1 plus x, and now use this, this is nothing but e power minus 1 by e power k, and this e power k here. So, this is nothing but e power minus 1 or 1 by e power a, 1 by e. Okay. So, what we have proved that if I repeated this experiment 1 e power k times, then the probability that C is bad in all iterations is 1 by e. Or in other words, the probability that, and what is my algorithm? My algorithm outputs yes whenever C is good, or whenever you find a colorful path, and it outputs no only if it is a no in all the iterations. So, my algorithm would have outputted no, like it would have given me a wrong answer with probability at most 1 by e, which is the probability that C was bad in all iterations, right? And now this is a constant probability, E is a constant, 2.718, right? So this is a randomized algorithm for the colorful k-path problem. So the algorithm is k-path, compute a coloring uniformly at random, run colorful k-path, and do this for e power k steps. We have just proved that if we do it for, and if it says yes, say yes, if it says no, repeat. And if it says no in all these steps, say no. This is the algorithm. And so, what is the running time of this k-path algorithm now? We know that the running time of the colorful k-path algorithm was k factorial into poly in n. So, what is the running time for the k-path algorithm? I'm basically, what am I doing? I'm computing a random coloring and running the colorful k-path algorithm, and I'm doing this e power k times, right? So what's the running time for the k-path problem? Yeah. So it is, I'm solving colorful k-path problem e power k times, and to compute a coloring uniformly at random, it's just some poly time, right? So basically this is basically e power k into k factorial. So we have solved this problem in this much time, but we have solved it like this is a randomized algorithm in the sense that in this much time there is an algorithm that runs in this much time, and if there was a k path in the graph, then it will give me a k path in the graph with probability at least 1 by e was the failure probability. So it would not give me the correct answer with probability at most 1 by e, it will give me the correct answer with probability at least 1 minus 1 by e, which is again some constant, right? So this is the algorithm for k-path, okay? So I'll just quickly tell you the theorem with which we can actually make this deterministic. So what is this theorem saying? It's saying that instead of, so basically where is the randomization coming? The randomization is coming from the fact that we are choosing this coloring uniformly at random, right? So I'll tell you a way, like I'll tell you what you can do about it, but before that, let me quickly let me just quickly say a couple of concluding remarks about color coding. So in the general setting, what is this color coding technique? Suppose you want to find some sort of a structure in the graph, okay? Like here we wanted to find a k path. Suppose you wanted to find a k cycle in the graph, or you wanted to find a particular a tree on k vertices in the graph. So some k size structure is what you want to find out. Then what you can do is you can in some sense reduce this problem of finding this k size structure to the problem of finding a colorful k structure. So here instead of finding a k path, we tried to find a colorful k path, right? So and it turns out that finding a colorful K path was easier in a sense. It was not very difficult, right, once we made some appropriate guesses. So similarly, so it turns out that finding colorful K path for, of course, it's not true for any general structure. For example, if the structure was a clique, if I wanted to ask you, can you find a clique on K vertices? You cannot find it. Forget color coding, you cannot find a clique on K vertices in f of k into polynomial in n time. I mean, that's a hardness result that people don't believe that such an algorithm exists for clique. So you can definitely not use color coding for clique. So it's not true that the colorful version of the problem is always easier, but for many problems it turns out that it is easier. In particular, for example, for K path we saw, you can try to see that you can try to get an algorithm for colorful case cycle also, for example. Okay, so that's an easy thing. So this is what I wanted to talk about. This is what I wanted to say about color coding technique. And now let me just quickly tell you a way to de-randomize it. I'll not be proving it, but I'll just tell you a theorem, and let's see if we can see that how we can use this theorem to de-randomize it. So what is this theorem? See, basically, where is the randomization coming again? It's the coloring that we are computing randomly, right? And what is the property of the coloring that we want? We want that this coloring, if there was a K path or a vertex set of, then it should color the vertices of this vertex set with distinct colors. That's the thing that we want, okay? Now, this theorem says that for any integers n and k, okay, there is a family with the following property. There is a family of functions which go from 1 to n to 1 to k. So what is this? This is a family, and the family contains some functions. What are these functions? These are some functions from 1 to n, whose domain is 1 to n and range is 1 to k, okay? It's a family of these functions which have a very, very nice property. What is this nice property? The nice property is that such that if you look at any k size subset of this set from 1 to n, there is a function that maps this set injectively into 1 to k. I'll write it down first. For any k size set S, subset of 1 to n. So basically, pick any k numbers from 1 to n and let S be the collection of those numbers. There exists a function, let's say f in this family, such that f is injective on S. What does it mean to say that f is injective on S? What is an injective function? What is a general injective function? 1 to 1. So for every element in the domain, there is a distinct element in the range to which it maps, right? So when I say a function is injective on S, in general the function f is from 1 to n to 1 to k. So in general it might not be injective, but if you just look at the function restricted to S, it is injective. That means for every element in S, it is giving it a distinct, it is mapping it to a distinct element from 1 to k, okay? So this is the property that we have in this family. And the good thing is, okay, so, wait. So, yeah, so what can you say about this family? Can you always come up with a family of functions which have this property? So what is this? I want to have a family of functions from 1 to n to 1 to k, whose domain is 1 to n and the range is 1 to k. And the property of this family is, if I give you any k size set, there is a function in the family which maps this set injectively. Okay, can you always forget this family, if I give you some set S, can you always find a function that maps this set injectively? Why, how? Sorry? Yeah, so see identity function, what is identity function on that set S? The other vertices could get something else, right? So you can, of course I can always give you a function that maps the set S injectively, right? I take the first vertex of S, map it to 1, second vertex of S, map it to 2, kth vertex of S, S is a case size subset, map it to key, and for the other vertices I don't care. Vertices as in, okay, here when I say vertices I'm meaning like, you can imagine these numbers 1 to n as being vertices v1 to vn, and these 1 to k as being the colors which are being given to these vertices, right? So you can always find an injective, a function that is injective on S, on any given set S, right? So can you always find such a family of functions? So what is this family of functions? You want to have one function for every set S of size k in this family, which is an injective. Sorry? It's a k size set. The size of set is exactly k. See, we just said for any set there is always a function. If I look at, if suppose I take all the functions from 1 to n to 1 to k, look at all the functions from 1 to n to 1 to k, right? So then if I give you any set S, a k size set, there is always a function in this family that is injective, right? Because as she said, you can, given a set S, I can always come up with a function that is injective on S, right? And now what have I taken in the family? I have taken all the functions, all possible functions from 1 to n to 1 to k in this family. So in particular, I would have taken all the functions, all the kind of functions that she proposed for a given S, right? Right? So basically such a family is no big deal. It always exists. But the good thing is, the good thing about the theorem is it says that you can find such a family. So the family that I proposed, it was the family of all functions from 1 to n to 1 to k. What will be the size of this family? How many functions are there from the set 1 to n to 1 to k? K power n. So the size of the family that I gave you is k power n. The good thing about this theorem is that it says there is such a family of size some e power k something. The numbers are not important. Look at it asymptotically what it is. So there is always a family whose size is this. Note that this is nothing but some f of k, okay, and this is some log n. Not just that, such a family f can be computed in time e of k, k power order log k into n log n, okay. So this is the theorem. So the good thing is again that the size of this family is bounded. Of course I can give you, there is always such a family, but this is the non-trivial part, that there is a family of this size and it can be computed in this much time. And again note that this is nothing but some function of f of k, like you don't have like. So now suppose I give you this theorem. I have given you this theorem in the sense that I have given you such a family f. And what is this? This is a family of functions from 1 to n. Imagine 1 to n as being the vertices of the graph and 1 to k as being the colors. So this is a family of functions from the vertices of the graph to 1 to k colors, which has this property. Now what can you do with this family? See, we are not trying to prove this theorem. I have already given you this theorem. So this family will have this property that no matter what, see what is this property? Basically the property of this family is no matter what k size subset you are talking about, okay, there is always a function in this family that is injective on S. That means this function maps the vertices of S with different colors, distinct colors, or in other words it makes this particular set S colorful. Right? So this is the property of this family. No, for any S that you give me, any set on k vertices that you give me, it will make it colorful. There is some function in the family that will make it colorful. So in particular, if I look at the set of k vertices that correspond to a k path in this graph, there will be a function in this family that will make it colorful. Now what can I do? Yes. So in the previous randomized algorithm, we were computing a coloring randomly with the hope that this will be a good coloring, in the sense this will make a k path colorful. Now instead of computing this coloring randomly, I look at each, so each of this function corresponds to a coloring, right? As I said, look at this side as the vertex set and these as the colors. So these functions are nothing but these colorings of the graph. So for every function in this family, you run this colorful k-path instance. And now let's see, if I do this for every function in this family and I say yes, if for any of the instance it says yes. So that is true, right? If it says yes, if it finds a colorful path, then there's a colorful path. And I say no if it is no for each such function. So for no matter what coloring I give, like no matter what function I give as input to the colorful k-path problem, it is saying no. Then can there be a k-path in the original graph? No, because if there was a k-path, then there would be some function that would be making it colorful, and hence when I would have solved that colorful k-path instance for that particular function, I should have got a yes. Because there was a k-path, this coloring made it colorful, and hence I should have been able to find a colorful k-path. So if I am not able to find a colorful k-path in any of these instances, you cannot have a k-path in the original graph, right? And now what will be the running time? The running time will be the number of functions for which we have to run the colorful k-path instance, right? And how many functions are there? That's the size of the family. So it is some e power k into k power order log k many times you are running the colorful k-path instance, and that is k factorial into k factorial, right? So it is this running time into k factorial time into some polynomial in n. Yeah, into polynomial in n time you can solve this colorful k-path problem. Again, note that this is some f of k function into polynomial in n. So it will be this function plus the time taken to compute the family also, because you have to compute the family, but that is again some f of k into poly n.